Hey, Year 12! Thanks for coming. It's nice to see you, Julian. Thanks for coming along. I'm just waiting for Winkit and Dixon, and then we'll be there, and then we can crack on. How's everyone doing? Is everyone keeping well? Keeping their social distance? How are people liking my my new login name with my chemistry mole? I was bored. I thought I'd draw something. I had to go at drawing it on my tablet as well. Not the easiest thing. It's far better to be able to draw with pencil. Where is everybody? I do realize we are 2 minutes early. Very artistic. Oh, thanks, Julian. So today we're going to be looking at alkenes, Julian. I think what I'll do is I will share my screen and we can crack on. Share screen. There we go. Let's go for that one. Julian, did you have a look at the free radical substitution questions? Today I was just looking at the year 12 document that I created for you guys. See if I can find it just to show you where. So the questions for this, for free radical substitution on that document are in a different place from where you'd expect them to be. We've been looking at alkanes. So if you go to your support sheet, you'll see this. There we go. There's your support sheet. I haven't hyperlinked in any of the super booklets yet. I will do them. But if you go down to haloalkanes, Julian, there's more there. So if you go to the haloalkane booklet, you'll get this. And you can see straight off the bat, actual exam-based questions. A bit of ozone. I might do that on a separate webinar just because it makes a bit more sense to do so. See if I can find an ozone question. Don't know why it's not loading all the way. It's because the booklet's so big. See if I get more pages this time. Don't know whether it starts because I'm using my bandwidth. Could be. Okay, well, considering... Oh, there we go. More questions this time. Right, there's ozone there. So I'll look at ozone as well. I'll do that at a later date. I'll do a separate webinar on ozone. I don't know whether or not any other teachers. Hey, Dixon's arrived. Hey, Dixon. Good to see you, dude. Just waiting for Winkit now. He's usually first here, and he's not in yet. So what I'm going to do, let's crack on with some chemistry. See if I can make those bits. Yeah, there we go. Oh, actually, no, do you know what I need to do? I need to actually go back. I need to do a new page. Winner, right. Oh, Tenzi. Hey, Tenzi. Good to see you, dude. Thanks for coming along. Really appreciate it. Right. So let's see if we can run some alkene chemistry. Yay. Right. Okay. So the title, you can make the notes. Title is Alkenes. Winkit. Way, he's in. Yeah, he's in. There we go. I like it. Good to see you, Winkit. Thanks for coming along. So I put the learning objectives on the description for the lesson on the YouTube channel. But I will put them into the lesson as well. I just always see the value in it. So in terms of learning objectives today, we are looking at, I need you guys to understand the bonding in alkenes. Bonding in alkenes. I also need you guys to be able to name alkenes. Name alkenes using, now I call it CIP. I'll put CIP. I'll tell you what that stands for. That stands for the Carn-Ingold Prelog. I'll write that underneath it. It's the Carn-Ingold Prelog. I know, so you don't actually ever need to quote CIP. You don't actually need to know the name. It'll always be in the question. But this here is to name what's called the EZ method. EZ naming. I will also talk a little bit about cis and trans because you guys need to know a little bit about cis and trans, but you don't need an awful lot on it. So I'm not too worried about it. I'm just going to be throwing in a little bit of that. Okay. So I think what we should first of all do is just let's do a couple of questions because you guys have been naming alkenes for ages. And so I think it's reasonable for us to be able to actually name basic alkenes. So let's do this one. Can everyone name this for me? Oh, sorry about that. Hang on. Can everyone have a go at naming this one? So all I'd like you to do, pause the video and give me your name. Yeah, pause the video, have a go at naming it, and then you can check with me. I'd like to think by this point, year 12, that you're able to give me that name fairly briskly, and you should recognize propene. Now, can I just point out, I'm not, that of course is the correct name. However, the name that I would like to think that you guys would be able to give me is prop-1-ene. Now, just to mention, technically, the 1 isn't needed. However, that doesn't mean that you shouldn't include it. Yeah, this is technically not required. However, it became very obvious to me as a teacher very early on when I was doing organics that students never really understood when it was or wasn't required. Now, what that means is there's a rule, which is put in all numbers. Just put them in. That way, because you can never get stung for putting in a number, but you will get stung more often if you forget a number. Obviously, the number does have to be the correct one, but it's better to include numbers. So in this case, prop-1-ene. Let's go for question number 2. Let's make it a little bit harder. Let's make it a little bit harder. Now, in this particular scenario, I'm doing one on purpose because Edexcel do really like this one. Yeah, don't forget to include all your numbers. Now, this technically isn't a family on its own. This is 2 families combined. Yeah, we have got an ene and we have got an ol group. So now, luckily, the ene is part of the stem name. Yeah. So pause it, have a go at naming it. But this one is important because there is a ranking. And I need you guys to understand and know that the alcohol group has a higher ranking than the alkene group does. What that means is in terms of numbers, we're going to number it in this direction. So what that means is we need all the numbers. This is prop. Prop, of course, comes from 3. Yeah, there's the prop. Next, it is an alkene. It's part of the stem name. And the alkene is between carbons number 2 and 3. Now, what that means is you've got 2 numbers to choose from. You always choose the lower number. So this is prop-2-ene. Now, the E at this point is about to disappear. The reason being is we now have an ol group. Yeah, and that's on number 1. So the E is going to vanish, and it's going to become a ene-1-ol. And yes, all numbers are required. The reason why, of course, question number 3, that was question number 2. Question number 3 is because of this guy. Have a go at naming it for me. Would be very much appreciated. Pause the video. Give me your name. So this is prop. Right, where's the number? Well, the ol group has the highest ranking, so I'm going to be numbering the carbons from this direction to make that as low as possible. So this is a prop-1-ene, 1-ol. And the ene has actually moved, so the 2 is required. I can also put the alcohol group on the second carbon, which means I definitely need that number as well. So just be aware that it is just better, it's better practice to be able to actually just include the numbers all the time. You'll be stung by it less. Any questions up till now? Let's do another one. Let's do another one. Can everyone have a go at naming this guy? Can everyone name that for me, please? There we go. Now, this, of course, is a trap. Not the hardest trap. I'll show you another trap in a second. But there is a trap in here. Longest chain is 4. Yeah, that is not a branch. It's just a bend in the chain. Yeah, so don't be fooled. It's very common. We're going to number it from this direction. Some students might ask, can I not do that? You can't. You've got to have the alkene as part of the main chain. So you can't use that route, even though it is still 4. Just got to be careful of that. Common question. So I've got a bute. This is a bute. Next, it's an alkene between 1 and 2. So it's a bute-1-ene. And then we've got a branch attachment. And this is a 2-methyl. And now you have to just put them together. 2-methyl, bute-1-ene. Very reasonable. Okay. Let's have a look at the next one. Question number 5. They're going to get steadily harder. Question 5. This is a very common Edexcel trick. I'll do that. Now, this is the first time where we're seeing a very important part of a name appear. So can everyone have a go at naming that for me, please? Again, I'm doing the same trick that I did before. I'm trying to show you guys the kind of games that the exam boards enjoy playing. And in this case, this little trick, by the way, can I just say I hate this trick. I really, really hate it. It's one of my least favorite games that they enjoy playing. It's just horrible chemistry. What they're doing is they're mixing displayed, showing all the bonds, with structural. It's a horrible mishmash of chemistry, which is, I just feel like it's just a little bit mean. But I can see the value in it. I can see the fact that there's a method in the madness here. What they're doing is they're checking to see that you understand the process of find your longest chain. And in this case, the longest chain is that one. It's all four. Neither of these two CH3 groups are actually branches. That's a butte. So let's straighten this out. It's one of the things that I like to do whenever I get these rather gross images. Yeah. And I'm just going to straighten that one out. And what you realize is that the longest chain is 4 and the double bond is between 2 and 3. So this is butene. Now there's an additional part of the name here. Now I've done this partly just for you guys to be able to demonstrate to me that you're doing that extra reading and that you're not sitting at home idly doing nothing. You know, since I created this sheet, since I created the epic sheet that I have for you guys, yeah, this thing, I'd like to think that you guys are being a bit more proactive, especially since you're being at home. I'd like to think that you guys are kind of getting to grips with applying yourself. Do you still pronounce the "een" or "n" when there is an ol? Yeah, it would be "enol." Technically, it's enol, but you wouldn't call it that. You'd call it an enol, Winkit. Good question. I love that you're doing that. You know, you're totally unnecessary, by the way. Yeah, it's not. You don't need to worry because you're never actually. This isn't like you're ever going to get a speaking exam. Yeah, I say it's an enol, even though the E is dropped. I still call it enol because what I'm trying to do there is I'm reinforcing the concept of what the families are. Yeah, I'm saying to myself, oh, I know it's an "een" and I know it's an "ol," even though the E drops off. So would anyone like to just jump in here and be able to give me the extension to the name here? So, and the reason being is the way it's orientated. And we're going to come to this in terms of isomerism. I just want to throw it out to the class and see if any of you guys know whether or not. If you don't worry about it. It's Z. Well done, Winkit. So this is classed as a Z isomer. Yeah, this is as the double bond can't rotate. Well done. Great job, Winkit. You're doing the extra reading. So proud of you. Thank you so much. Really, really pleased. Higher priority on the same side. Well done. Great job. So you're running the Carnegie pre-log there for me already, which is outstanding. I will just give you a little bit of detail onto that. That we could have actually given it an alternative name as well. You could have called this cis. This is also cis-butyrene. That is also allowed. The reason, and by the way, I'll explain why in a minute. When you can and can't use cis. Now, can I just point out that Edexcel primarily want you to be using EZ isomerism, using the Carnegie pre-log. However, it says in your specification that you need to understand when the cis naming system, cis-trans naming system falls apart. So we'll come to this now. So, okay. So we can now go, let's do a subtitle, please, of bonding. Cis is when same group, but if we have Cl and I and F. Yes, that's correct, Winkit. Yeah, that's correct. So let's do bonding. Bonding in alkenes. Okay, so there's a couple of key things here. Now, if you were taking IB, I'd have to go to town on this bonding. And it's actually very tempting at this point just to incorporate a little bit of the IB understanding. But it's not required for Edexcel. So it's relatively straightforward. What you guys need to, if we look, each carbon atom, we know that carbon atoms form 4 bonds. Carbon atoms make 4 bonds. Now there are times when this rule is broken. Graphite is a great example. I should put those in. Exceptions. And you need to kind of know them. Exceptions. We've got graphite when it only makes 3. We've also got carbocation intermediates. We're going to see that with alkenes shortly. Yeah, that one is definitely going to make an appearance. So is the graphite. I mean, graphite you've learned since GCSE. Are there any other examples when you see it? Yes, I'm going to say SN. I need to be careful here. This is SN2 mechanism as well. Now, technically, this is part of A2 for Edexcel. And so I'll put A2, see later notes. A2 notes. But I might even introduce you just briefly to that. SN2 mechanism, and this is also an intermediate. Yeah. Mechanism. I'll put mechanism intermediate. Cool. Okay, so we know that carbon makes 4 bonds. Now, can I just point out, in terms of the understanding of this, that's a really strange thing. And you also pick up a shape at this point. And that shape is super important. This shape, yeah, this shape here is a tetrahedral. This is a four-sided shape. Yeah, 4-sided pyramid, if you like. So we call this a tetrahedral. So, okay, and it'd be quite nice just for us to then recognize other bits of detail here. Like, we know what the shape is called. The shape is called tetrahedral. And we also need to know its bond angles are super important of 109.5. Guys, you can actually, by the way, you can actually work that out mathematically. And I think Winkit tried to actually explain it to me once, and I got a bit lost with the maths. But that's a number you just ought to recognize and learn. That's worthwhile doing that. So, okay. So the question is, how is this possible? Now, I'm going a little bit beyond what you now need to know. This is IB higher. Now, this will be really great for anybody who goes on to do chemistry further. That is EZ, right? Yes, it is EZ. As I said, I'll give you a bit more detail on that, Winkit, later on. But for IB higher, one of the things that you guys have to explain in IB higher is you need to explain how it's possible for it to make those 4 bonds, because carbon is a very interesting element. Carbon on the periodic table is element number 6. It's got 6 electrons and 6 protons. Now, we can write its configuration, 1s2. Now, I'm just going to do a bit of practice on this one. Yeah, because it's always great to reinforce that good practice. So if I do a full screen snip, let's just see if we can build carbon's configuration. So number 1, hydrogen should be here. Yeah, and helium should be here. But they were moved because of their properties and how they go with their particular groups. This here, I'm going to do this in a color. This here is called the S block. This is called the S block. All the elements in there have their outermost electrons in the S subshell. Yeah, this block here is called the D block. Yeah, this is the D block. And then this block here is the P block. Helium isn't a P block element, by the way. Yeah, that's a P block. So we're going to read off carbon. So when you go through this, the row number is 1. I should try and actually put it here. 1, 2, 3, 4, 5, etc. So this here is the 1s2. This is the 1s subshell. And there are 2 people in it. Yep, so that's 1s2. Now, helium is, of course, not really there. It's over here. So that means we've read the table this way across it, and then we've reached the end, so we then go back again, and we go in from this way. So this is the 2s, and there are 2 people in it. Yeah, so that's the 2s2. And then you cross over the gap, and you reach this is the 2p, and we get to carbon 1 and 2. So we're reading the table. So the EC, the full electronic configuration of carbon is 1s2, 2s2, 2p6. Now we can now translate that to an orbital box diagram. So we've got the 1s, 2s2, and then we hit the 2p. And the 2p is 3 orbitals, and that's what carbon's looks like. And then just gonna continue it up there. Dot, 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 dot. Yeah. Anyway, don't really need those. So this is carbon's arrangement. Now, if you look at carbon's arrangement, you would expect carbon not to make 4 bonds. You would expect it to make 3 bonds, but one of them would actually be dative. Yeah, that's what we would expect. We would expect carbon to, because it's got 3 electrons in its outer, it's got technically 4 electrons, because this is the second shell. This is the second energy level. I'll put energy level, energy love. And people go, oh, it can make 4 because it's got 4 electrons in its outer shell. Yeah, but its actual outer energy level is actually the 2p, and there's only 2 people in it. So the 2s underneath is full, yeah, but the 2p has only got 3 people in it. So you would expect it, sorry, it's only got 2 people in it. You'd expect it to make 2 bonds, 2 standard bonds, but then be able to also make a dative. That's what we would expect, because you'd expect it, I'm going to do that in red on here. Normal bond, dot and cross. Normal bond, dot and cross. And then you'd make a dative with both people coming from the next one. That's what you'd expect. But we all know here, we all know that carbon actually makes 4. Well, the question is, how is that possible? And the reason why is it actually does a really cool thing called hybridization. Just going to redraw out a second version of this. So this is the 1s, this is the 2s, this is the 2p, and this is the 3s. So what actually happens is carbon does something really cool, which it takes one of the electrons from the 2s and it promotes it up into the 2p. The 3s doesn't get used. We're just basing it all around the second energy level. And what you actually create is a hybrid shell. What that results in is what's called a hybrid, which looks like this. This is an sp3 hybrid. I think the 3 is actually lowercase. It is. An sp3 hybrid. And now what you notice is it can now make 4 standard covalent bonds. Now, why is this useful in terms of shape? The reason being is the 2s is a spherical shape. The 2p is made of a py, a px, and a pz, which is going towards and away from us. So this is a pz. And what you'd realize is, how is it possible to get tetrahedral from that shape? Well, you've got 4 orbitals, and here's the cool bit. When you blend all of these together, you create 4 orbitals that look like this, with a little tail. You don't have a, by the way, this is hybridization. This is outside of the Edexcel specification, but it's just really good to do it. Those there are sp3 hybrid orbitals, 4 of them. And the great thing is these can be put together. And if you put them together, you get this shape. You get the tetrahedral that everyone recognizes. There we go. We don't really care about the baby orbit, the baby lobes. By the way, this is a head lobe. This is the head lobe, I believe. And this is the tail lobe. And we never talk about the tail. We don't bother. It's not needed. Yeah, it's tiny in an sp3 hybrid. And now you get, as a result of that, you end up with your really cool tetrahedral shape. Now, what that then means is if you take let's go ethane. So what's this now look like if you put it in a compound? So each carbon is hybridized, and what you get is this tetrahedral orbital image. Yeah, and then you've got a H at the end, and H, of course, is only an S1, which means it's a circle. Yeah, here are the H's with a dot and cross in the gap. And then you've got another carbon over here. Didn't want to make it longer, I want it to be the same. Sorry, trying my best here, folks. There we go, that'll do. And then you've got the other lobes that are giving us the hydrogen bonds. There we go. There we go. So this is the shape you get for ethane. Now, this, and then in the overlap. Now, these kind of bonds, these covalent bonds here, are all what are called sigma bonds. I don't know, that keyboard really annoys me. So these bonds are called sigma bonds. And this is the Greek letter for sigma. These are called sigma bonds. And sigma bonds, sigma bonds are defined as head-on overlap of orbitals. Head-on overlap of orbitals. Yeah, so it's just literally the head of that orbital forming a bond with another head. Yeah. That there is a head-on overlap, a sigma bond. There you go. So how is it possible then to get an alkene in this scenario? So, okay, if we're going to turn this image into an alkene, what we're going to need to do is we're going to need, does it then form a pi bond? Yes, it does, wink it. So there's ethane. So what does ethene look like? So ethene, I'm actually going to do what you guys can't. I'm going to go, don't know why it's doing that. My laptop does have its idiosyncrasies. Copy. Oh, that's entertaining. No. Let's try that one more time. Try that one more time. Copy. Paste. There we go. There we go. So there's, I hate the fact that the H is a bigger size. Makes me feel a little bit happier. Not by much. I'm just trying to reduce the size to make it just me being faffy. And that one's gone missing. There we go. So how can I now turn this into ethene? Well, what we know is we've been drawing this image for years. Yeah. So we need to take away two hydrogens, and it's one from each. So we take away the hydrogens. What I now need to also do is take away its electron. So the circle was carbon's electron. I'll see if I can take away that one as well. There we go. Now, when you do this, what you'd like to imagine is that this thing can then fold over like that, like flour would, and you're going to get this, once again, this other head-on overlap. But that cannot be the case. The reason being is you'd have a pair of electrons. You'd have a pair of electrons sitting on top of the other. Now, this is why whenever you do these kind of images, you know, teachers don't say do this because that's just madness. That cannot happen. The reason being is electrons repel each other. We all know this. And you'd be going from a bond angle of 109.5 degrees to 0. That's what you'd be trying to do. So it can't do that. So it does something really clever. Now, I talked about hybridization in terms of the boxes. Yeah, I did this. So it now goes through a second step. So when it forms an alkene and the H's are removed, here's what happens next. This sp3 hybrid, which looks like this, and it now has a scenario which is that. That's its new scenario. Each carbon is in the same situation. That applies to both of them. Suddenly realized I don't really like that. Oh, undo. There we go. I'm going to do that in color because it's nicer. That there applies to both carbon atoms. So it goes into another situation, which is really clever. What it now does is it fragments. And it splits off. I now end up with an sp2 hybrid, which is this shape, which is now this shape. It becomes trigonal planar, which is rather cool. That explains, so all trigonal planars are in an sp2 hybridized state. So that there becomes trigonal planar. Just to tell you, there's also a bit of detail there. First year degree, the actual tail lobes increase because I've now only got, I've got an S and a PX and a PY. Whoa, I made a mess of that. PX and a PY. And it means that the S has got a greater percentage share in that, which means you actually end up with extended tail lobe. This is the head lobe, and then the tail lobe is slightly larger. But luckily, the trigonal planar arrangement can actually compensate for that, which is good. So it's just cool to know that. I'm just going as first year degree chem, if anybody's interested. But the question is, what this sp2 is, this is now an S. Yeah, it's an S. Just looks like those lines are flat, and they're not. This it's a sphere. I've got an S, and I've got a P. I've actually technically got the PX and the PZ still kept. Yeah, that's an sp2 hybrid. And what now splits off is the PY. Now, the reason why it does that is because the PY, so what's the new image that I now get? I now get this image for ethene. I've got standard head-on overlap in the middle. So this is a sigma bond. I've got a sigma in between the two carbons. I've got a trigonal planar arrangement. I'm going to try and draw this three-dimensionally. So that's like flat, and this one's going to come out at us. Yeah. I'm trying to make it look like it's three-dimensional. Yeah. So it's flat. This is trigonal planar. So I'm desperately trying to do this well. There's that one, and then this one coming out at you. Yeah. And I'll try and make that look a little bit more like I'm actually including those things in my drawing. Trying very hard here. There we go. So this is now flat. By the way, these are the same size. You all know that these are the same size in reality. Yeah. I'm just desperately trying to make it look like it's 3D and it's flat. Yeah. So, and then you've got the H's attached here and here. So what that means is, number one, anything that contains a double bond, any double bond, yeah, is actually in an sp2 hybridized state, and it will be planar. Anything. That includes this structure, yeah, the aldehyde group. This is planar around that structure. Yeah, this, I can redraw that for you. Yeah, that is planar. Yeah, it's flat. Yeah, that's a trigonal planar around that particular structure. That structure. Doing my best to draw these. So the question is, where's the PY gone? So the PY has now done this. Let's now split off the PY. I'm going to change my color. So the PY has split off to give me that picture. I've got to be careful here because I've got to make it large enough to be able to see this. So I need it to actually, sorry folks, I've made the sigma bond in between the carbons too long. I apologize about that. Right. So what happens is the PYs that split off now get sideways overlap. And this is called a pi bond. So in alkenes, there's actually two types of bonds going on. We have got, I'll do my best to draw them. So in alkenes, I shouldn't really put this with previous notes, really, should I? So in an alkene, when you draw, so this is kind of overall, yeah? So what we see is we actually have, when you're writing it and drawing it like this, one of those bonds, one of the bonds is a sigma, yeah? One of them is a sigma bond, and the other one is a pi bond. And you get this rather lovely sideways. So what I'm now going to do is I think it makes total sense. I know that my drawings are amazing. I mean, amazing. But I just want to show you, a really nice image. Ethene pi bond. And yes, it's spelled just like that. And that's the picture I want you to have in your head. Recognizing, I want to have a really nice one. Yeah, they blend together. It's really neat. Trying to find a picture that I really kind of have an affinity for. I quite like that one. That one's quite a nice one. So we get this cloud of electrons above and below. I'm actually going to cut that, I think. I may as well. Don't see why I shouldn't. The pi bond is circled in blue. I'm going to go copy image. Don't know if this is going to work. Paste image. Don't know if it's going to work. It might do, or it might not. No, as the case may be. Let's try that again. This time I'll snip it. Yeah, new snip. I'll just snip that. There we go. And then go edit, copy, and that will then work. So theirs is just a better image of what I've been attempting to draw. Yeah, which is kind of nice. It's cool to understand this. This concept of sideways overlap is really important in chemistry because later on in A2, this confers a whole load of additional properties. But it's really cool to have a good understanding of hybridization and how this contributes to kind of like the actual structure of the molecule, how it makes it become flat, which is really nice. There's great chemistry in here, folks, really good chemistry. I don't know why it was flagging that and flashing it. So what does this mean in terms of the bonding or the particular molecule in terms of isomerism? Can everyone put a little title, please, of, I'm going to zoom in a bit more actually on this, make my pen small, I quite prefer that. Can you put a little subtitle of geometrical isomerism? Now, I'm going to now mention that there is a very, very bad habit out there for A-level chemists, a really bad habit. And that habit is to call this EZ isomerism. Yeah, this is a really bad habit. This is not a thing. No, that will lose you the mark every time. I don't know what internet websites is saying this to people, but it's garbage. Yeah, the only answer is this is geometrical isomerism, and the definition of geo is the same for any, we know that there's the two S's, structural and stereo, it's part of stereo. This is same structural formula, same structural formulae, but different arrangements of atoms in space. Ugh. Too many words. Different arrangements of atoms in space. So, okay. Now that we've got the definition, how can this impact us for alkenes? Gonna make my pen a bit thicker. The reason why is the double bond has an impact on how the molecules are moving. You see, in a single bond, what we actually realize, I'm going to put on an actual, I'm going to do that. I'm going to do this. But in reality, and I've put on, that's chloroethane, this bond, the single bond in the center, is actually rotating. This entire group is rotating. What that means is, this is why that picture there, so this is rotating. And this is why if you were to draw this, yeah, all the rest of them will be good. I'm on the internet, I should be good. Yeah, if I draw that, that is the same as this. There is no difference. Yeah, we just know that, oh, it's on the same carbon. They are the same thing. This is the same as this. That is because of one reason. The bond in reality is allowing it to rotate. You can't say turn, you can't say spin, you can't say turn. The only word you're allowed to say is rotate. However, if you have an alkene, you end up with a rather different scenario. We know that these are now trigonal planar, yeah? And your pi bond above and below prevents it from rotating. I'm going to circle that in blue. Do you know what I don't like that. I've just made it messy. The pi bond, which is there, if you want, I can do it like this. Come on, Mr. Duncan. The pi bond, that sideways overlap, now prevents it from rotating. Will rotate clockwise or anti-clockwise? Both, Dixon. Great question. The answer is it'll be rotating randomly, and it will even stop and rotate in other directions depending upon collisions. In one axis, yes, only in one axis. Yeah. Yeah, I mean, don't get me wrong, the whole molecules will be turning, will be spinning technically in all axes, but that bond is in rotation on one axis. So we now need to know, due to pi bond, double bonds cannot rotate. And as I said, you can't use any other word than rotate. Now, what that means is there's a consequence. What that means is, because it's flat, and because it can't rotate, there are differences. If I put a Cl here, and a H there, and a H here, and a Cl here, that is different compared to this guy. The reason being is it has been locked in its spatial position. Triple bonds can't rotate as well. That's correct, they can't. Absolutely right, Winkit. Triple bonds cannot rotate. But that doesn't matter. We never talk about that, because if you've got a triple bond, you're only ever gonna have one attachment anyway, and you can't get a difference in spatial arrangement because you could just rotate the entire molecule around. That there is the same as that one, because all I've done it is spun the entire molecule round on its x-axis. That makes sense. Does that make sense? I hope so. Anyway, good question though. But no, you're right, it doesn't rotate. It doesn't. It is fixed. Okay, next. Triple bonds are even cooler as well. That's got more hybridization stuff going on. SP hybridization rather than SP2. So we've got two people here, And the first naming system that was applied to this, the first naming system was what was called cis and trans. Yeah. So the naming system for this was called cis and trans. And cis means same, and trans means opposite. Opposite. That's what it means. Trans, or different, if you like. I don't think that's actually entirely true. Damn, I've got to check my Greek. Cis. Word. Origin. Origin. Cis. Etymology of the word cis, meaning on the side of. Meaning across. Trans meaning across from. Ah, on this side of. Huh. Isn't that interesting? On this side and on opposite side. That's what it actually means. So we could then say that this guy, let's call this A and this B. We would now say that as a result of this, we'd go A would be trans 1,2-dichloroethene. And the other one, B, would be cis 1,2-dichloroethene. Just to point out, they tend, those words just literally go before it. Trans and cis. There we go. Maybe they go in a bracket. I don't know, the EZs do. I prefer that. You're telling them a spatial arrangement rather than the dash. I don't like the dash. There we go, that's better. So we've got cis and trans isomerism, but there was a limitation. There is a limit to this naming setup. The reason being is this guy. Right. So cis and trans, this one can't be named cis trans. The reason being is there's no two groups that are the same. They are all independent groups. There is no two people alike. So we now needed a new system, and we invented CIP, the Carn-Ingold prelog, which goes on ranking. So this is the Carn-Ingold prelog. Now I'm going to, by the way, Edexcel have never asked you to actually do a full explanation using Carn-Ingold prelog, but I'm going to teach it anyway. Yeah, so what we say is consider the carbon on the right. Sorry. Okay, sure, I've said right, let's stick with right. So, consider carbon on right. Attachments are iodine, atomic number, give me a minute, 56, and bromine, atomic number 35. Periodic table, please. Iodine 53, bromine 35. What did I say? Suddenly realized there's a really easy way to remember that. Notice the two numbers are opposites. Never noticed that before. Something new to add to my repertoire. I know bromine, that's easy. But iodine, I never really talked about her very much. Now, attachments are, what that means is iodine, bigger atomic number, so higher priority. Higher priority. Done. Next, consider carbon on left. Attachments, fluorine number 19 and chlorine number 17. No, fluorine number 9, chlorine number 17. Chlorine, bigger atomic number. I'll just do it. Bigger atomic number, so high priority. High priority. So what we can now do is apply those. Oh, have I just got them the wrong way? So sorry. Consider the carbon on the right. Iodine and chlorine. I apologize, folks. Chlorine's number 17. Yeah, iodine is still higher. And then we've got fluorine and... I'm sorry. I apologize. And bromine 35. So bromine now. There you go. Bromine now takes priority. Sorry, folks. I just didn't look back at it properly. It came out in the wash. Wonder who spotted it before I did. So we've now got high priority, high priority, low priority, high priority, low priority, and the highs are on opposite side. So it's now an E. Last bit, high priorities, high priority atoms on opposite side, on opposite side of molecule. So therefore it is an E. Let's build the name. In fact, guys, I want you to pause the video and have a go at this for me. That would be great. Pause it, have a go. Gonna zoom right in. We can now name this properly. Step number 1, ethene. Step number 2, attachments. Needs to be done alphabetically. Yeah. So, and I'm going to count this from that side. People often go, which one do I... Is the high priority then decided by the relative atomic mass of the branch? No, it's not, Winkit. I'll come to that in a minute. Good question, though. Yeah, this is a bromo. A 1 bromo, alphabetical, 2 chloro. People often ask me, how do you know which carbon atom is the ranked highest? Well, alphabetical order, this one's going to go first. These are all ranked the same because they're all halos. Yeah, and that's then going to be a, what's that? B, C, D, E, F, 1 fluoro. 1 fluoro. It's not spelled like the word flower. 2 iodo. Put them all together. So 2, and you need to stick in an E there. So E, 1 bromo. 1 bromo, 2 chloro. Yes, it's a nightmare. 1 fluoro. 2 iodo. Ethene, and it's an E at the beginning. And we're done. So guys, that's finished off my lesson. Look at that, pretty much dead on an hour. And in terms of my learning objectives, we have covered the bonding in alkenes, described how they're planar, even gone into hybridization, sp3 and sp2, sp3 for standard 4 bonds, sp2 for double bonds, which makes it planar, really nice. And now we've done the Carningol prelog, However, Winkit has just asked one last question. I know I've overrun my lesson. You guys are probably going to need to go. Yeah. If I've got this scenario, and I put a CL there, there we go. So how do I know which one it's going to be? So number one, I think everyone here, oh, hang on a sec. I'll make this harder. I'll make it harder. There we go. Okay, so which one's the ranking? So consider the carbon on the left. 17 high, 1 low. Next, consider the carbon on the right. 6. They have the same. Go to the next atom. 1, 17. Right. So this one's now going to be high, and that's low. And therefore, it's going to be an E. I hope that helps Winkit. Right, guys? That brings us to the end of the lesson. I'm sorry that I've overrun by a few minutes. See if I can bring back. Muted myself again. There we go. Right, guys, I'll leave you be. I hope you have a nice rest of your day. Take care of yourselves, guys. I'll see you soon.